The dominant marketing narrative surrounding 5G is consumer-focused, the promise of faster smartphones and seamless 4K video streaming. But the global telecommunications industry did not rebuild its entire physical infrastructure from the ground up to incrementally improve human social media consumption. Human mobile data usage is actually an architectural afterthought in the modern cellular topology. Look at this photograph of large blue industrial gantry cranes at a shipping port. The true target of the infrastructure overhaul is massive, automated enterprise operations like this, which require continuous, machine-scale data processing. 5G is a unified, virtualized baseplate engineered specifically to handle the density, latency, and scale of enterprise IoT. To understand how this works, network architects must stop looking at mobile devices and start analyzing the physical bottlenecks of machine-to-machine communication. This new architecture solves three contradictory network demands. Telecommunications engineers refer to this framework as the three-headed dragon. The first head is enhanced mobile broadband, or EMBB. This is the requirement for massive data throughput. The second head is massive machine type communications, or MMTC. This dictates the network's ability to support an exponentially high density of individual endpoints. And the third head is ultra-reliable low-latency communications, or URLLC, requiring instantaneous fail-proof reaction times. We can plot these competing demands on a three-axis radar chart. Legacy LTE networks could only satisfy one of these axes at a time. Optimizing the radio frequencies for bandwidth meant sacrificing density, and optimizing for density compromised latency. The core engineering tension of 5G is executing all three. The network must process an 8K video stream, 100,000 agricultural sensors, and a robotic surgical arm simultaneously on a single physical wireless infrastructure without catastrophic failure. The primary bottleneck of 4G architecture becomes obvious under extreme device density. In what engineers call the stadium problem, legacy networks degrade rapidly when pushed past approximately 2,000 concurrent devices per square kilometer. The MMTC specification in 5G requires the network to handle 1 million devices per square kilometer, a 500-fold increase in scale. Look at this cellular telecommunications tower. Notice the multiple rectangular antenna panels. This 500 times scale increase is not achieved through software alone. It requires this structural hardware redesign at the base station. This physical layer solution is known as massive MIMO, standing for multiple input, multiple output. Traditional 4G omnidirectional broadcasting floods an area with RF waves. When too many devices attempt to communicate simultaneously, these waves collide and cause destructive interference. This conceptual diagram demonstrates how massive MIMO operates. Instead of a flood, the dense antenna array computes signal reflections and executes multipath propagation, firing highly directed, individual RF beams to distinct scattered sensor nodes. This targeted beamforming allows the network to serve multiple endpoints on the exact same frequency without signal collision. Massive MIMO solves the density problem by converting the physical airwaves from the congested omnidirectional flood into millions of isolated computational pathways. The second major constraint is latency, the domain of URLLC. This image of a large yellow industrial robotic arm working on a metal component establishes the benchmark. For the tactile internet, where machines transmit physical touch and reaction, network latency must drop below human perception. Even if RF transmission is optimized perfectly, the speed of light over fiber optic backhaul introduces an unbreakable physical speed limit. Trace a data packet on this map. Traditionally, it travels from device, cell tower, cloud server, and back. The timer counts up. 5G integrates computing power directly into the cell tower. The packet processes instantly at this embedded node and returns. The raw data for critical industrial operations never actually touches the core consumer internet. The AI inference happens locally at the edge. URLLC is achieved by physically moving the computing brain out of the cloud and placing it immediately adjacent to the machine. The final architectural challenge is running massive swarms of low-power sensors and high-stakes, ultra-low-latency robotics on the exact same cell tower simultaneously. On a traditional network, a massive influx of sensor pings causes packet collisions. If those collisions delay robotic telemetry, it leads to physical accidents. The software-defined solution that unifies the 5G baseplate is network slicing. Look at this diagram. A physical RF pipeline is partitioned into 3 color-coded virtual tunnels. Architects assign different quality of service parameters to each. One prioritizes bandwidth, one prioritizes scale, and one is shielded for strict latency. Each slice operates as a bespoke end-to-end local area network, tailored to its specific IoT payload. A traffic spike in the high bandwidth slice cannot physically impact the latency of the URLLC slice, despite sharing the exact same hardware. Network slicing tames the three-headed dragon. It proves that 5G operates as a highly adaptable virtualized environment, rather than a static radio broadcast. Zooming out from the mechanics of the cell tower, we can view the macro impact on a modern smart city or sprawling enterprise campus. Historically, securing and scaling a massive industrial site required laying miles of physical proprietary cabling, like Ethernet or CAN bus. Watch as the web of underground physical cables dissolves, replaced by targeted glowing beams connecting directly from a central tower to the buildings. This architecture is known as last-mile fixed wireless access. By combining massive MIMO beamforming with network slicing, enterprises replace physical infrastructure with over-the-air connections capable of carrying secure, gigabit-level loads. 5G transitions the cellular network from a dumb communications pipe into a distributed, global computing environment. For the modern network architect, the rigid boundary between the local edge device and the global cloud has been erased by this infrastructure. 5G was never engineered to make the consumer smartphone faster. It was built to serve as the invisible, high-density central nervous system for the next century of automated global industry.